Hi everyone, and welcome back to physics. This is Mrs. Hutchinson, and today we're going to continue with Newton's laws of motion, but we're really going to talk about the different types of forces that we encounter during motion. So, the first type of motion, or the first type of force, rather, that we deal with is one that we've actually already talked about. We discussed it in a previous video, the weight force. So, mass, weight, volume, really, what's the difference between all of those terms? Now, a lot of people use mass and weight interchangeably, but mass is simply the measure of the quantity of matter that an object possesses. In other words, your mass on Earth will be the same as the mass on the moon because you still have the same amount of matter making up your body. The more mass an object has, the more it resists having its motion change, so the more inertia it has. Volume, however, is the amount of space that an object actually occupies. So really, what's the difference between mass and weight? So, weight is actually the force between any object with mass and the Earth's surface. In other words, your weight will always point towards the center of the Earth. And to calculate your weight, you have to take your mass and multiply it by the acceleration due to gravity. And for us, it's the acceleration due to gravity on Earth. So, when you're calculating your weight on Earth or your weight on the moon, there's different accelerations due to gravity. The moon has a lot less of an acceleration due to gravity, which is why you will weigh less. However, your mass on Earth or on the moon would be the same. As soon as you come back to Earth from the moon, you're going to weigh the same that you did before, providing you didn't lose a ton of weight in space, which would stink, but or be a good thing. I mean, it's up to you. But it is important to realize that the weight is actually a force between an object with mass and the Earth's surface, or the acceleration due to gravity. We've seen this law before. I wanted to show you here again, where you can find your equation for our weight force. Our weight force is depicted by Fg, and the way that I typically like to write it is Fg equals mg. I'm not really sure why they write it in the other manner on our reference tables, but the way you'll see me write it is Fg equals mg, where m is actually our mass, g is our acceleration due to gravity, which is 9.8 meters per second squared on Earth, and Fg is our weight force. Our weight force has a unit of newtons. Any force has a unit of newtons, just so you are aware. So let's try this particular problem. What is the weight of a man that has a mass of 70 kilograms? Now, where people tend to get confused is that they see that you're given a mass and you're asked for the weight. And so many people just simply write, okay, well, your weight is 70 kilograms. No, your weight means your weight force, your weight in newtons. So now we simply have to solve for our actual Fg. So let's write our givens. We know our mass is 70 kilograms. They didn't give us our acceleration due to gravity. If it's not given, it is assumed to be on Earth. So our acceleration due to gravity is 9.8 meters per second squared. Our wanted is our weight force, so Fg. Our equation, pretty simple. Fg equals mg. Substitution, Fg equals 70 kilograms times 9.8 meters per second squared. And then our answer is simply 686 newtons. Not too shabby, not too bad, not too difficult. Again, things you want to remember if your mass is not given to you in kilograms, make sure that you convert it to kilograms because a newton is a kilogram meter per second squared. So just be aware of that. But this isn't so bad. Let's try another example problem. So a man is building a bench that he wants to be able to support a person with a mass of 150 kilograms. What force must the bench be able to withstand? So, the man is going to be sitting on the bench. That means that that bench needs to be able to support his weight, or his weight force. So, let's go ahead and solve this. Let's write down our givens. So we've got our mass is 150 kilograms. And again, it doesn't say that we're not on Earth, so our acceleration due to gravity is 9.8 meters per second squared. Our wanted is our weight force, because that bench needs to be able to support our weight, or this man's weight. Our equation, Fg equals mg. Substitution. So let's substitute everything in. We've got 150 kilograms times 9.8 meters per second squared. And our final answer turns out to be Fg equals 1470 newtons. And that is our answer. Again, not too bad, not a terribly difficult equation, which is kind of nice. So what I want you to do now is I'm going to read question 8, or the next question, to you, and then I want you to pause the video and try it on your own. So it states, the man in problem 5 traveled to another planet. His weight on this planet was 310 newtons. Find what is the acceleration due to gravity on this planet. In other words, remember, that man had a mass of 70 kilograms. So given all of this information, what I want you to do is pause the video and try to solve for the acceleration due to gravity on this planet. Hopefully you pause the video. What I want you to do now, or what I'm going to do, is show you how to do this particular problem. So we've got our given here. His weight on this planet is 310 newtons, so that means that we're talking about his force of gravity, 310 newtons. His mass was given to us in a prior problem of 70 kilograms. Our wanted is our acceleration due to gravity for this particular planet. Our equation, Fg equals mg. Substitution. So we plug everything in, we get 310 newtons equals 70 kilograms times our acceleration due to gravity. And we solve for our acceleration due to gravity, and we get 4.43 meters per second squared. So hopefully that's what you got. If you didn't get that, you can pause the video and check it out again. Make sure that you plugged in everything incorrectly. Maybe you had a little algebraic mistake. If you got it right, let's move on to our next type of force. So our next type of force is known as the normal force. The normal force is depicted by this representation, F sub n, that equals our normal force. And again, our units for any type of force are going to be newtons. So really, what is the normal force? Well, when a body exerts a force on a surface, the body experiences a normal force, which is by definition perpendicular to the surface. In other words, when you are sitting in your chair right now, you are experiencing a normal force. You have your weight force pushing down towards the center of the earth, and you've got your normal force pushing back up on you. So here is your here's your chair. That's a terrible drawing. Here's you, I'm not really sure where to put your arms. And let's put a foot there. Yep, that's terribly disproportional. But anyway, so you're sitting in your chair. Your weight force points straight down, so Fg points straight down towards the center of the earth. And your normal force is going to be perpendicular to the surface. Perpendicular to the surface with which you are sitting. So your normal force is going to point up. If that normal force were not there, you would fall straight through your chair every single time. You wouldn't have anything opposing your force of gravity. So that's why we are experiencing a normal force every time a body is resting on a surface. Now, if a body is resting on a horizontal surface, the normal force is that such that it balances the weight force. So if we take a look at our free body diagram. Now, what is a free body diagram? A free body diagram depicts accurately the directions in which forces or vectors will point. So what we have is we have a dot that depicts our object, and then we've got our forces represented in our free body diagram here. So let me make that dot gigantic. We've got our weight force pointing down, and if this particular block is simply resting on our table here, that means that our normal force must balance out our weight force. Because if it's resting, we have to have balanced forces. There's no unbalanced force acting on this because it's not moving anywhere. So what we can say is when we're resting on a horizontal surface, our normal force winds up being equal to our force of gravity. So you sitting in the chair, your weight force is equal to the normal force with which the chair is pushing you upwards. Now, again, if you weigh a little more, then that chair is going to be pushing a little harder on you to keep you resting. That's all that's saying. Now, since the normal force balances the gravitational force and the object is at rest, we can say that the object has no net force. Because, again, think of it in terms of a tug-of-war. Our normal force is pulling upward with the same amount of force as our force of gravity. So if we just assign arbitrary values, and we say that, okay, our weight force is 500 newtons, then that means our normal force is pointing in the opposite direction, but has the same magnitude. So again, if you're in a tug-of-war with yourself, who's winning? Nobody. There's no net force. So let's describe this a little further. We can describe the magnitude of the normal force in, I said the above diagram, but what I actually did was in this diagram here, by applying Newton's second law as follows. So the net force is actually the difference between opposing forces. So, which makes sense, right? Because your net force is the force, the overall force on the object. So we can say that we're taking the difference between our opposing forces. Again, if we're putting an arbitrary value on this, we can state that our normal force is equal to 500 newtons in the upward direction, because this is a vector, so a direction is associated with it, and our gravitational force is pushing 500 newtons down. So when we take the difference between these opposing forces, the one that's pointing up and one that's pointing down, you're going to get a difference of 0, an F net of 0. Right? So we get 500 minus 500. Your net force is equal to 0 newtons. Because we stated that we have no unbalanced force. This is at rest, so the forces are opposite of one another. In other words, since our force of gravity is equal to our normal force, we can state that our normal force winds up being equal to our weight itself, just in opposite directions. So things I want you to think about. it is important to note that this above generalization, that this right here, the fact that our normal force will always be equal and opposite to our gravitational force, only works if the normal force is directed upward or directly opposite that of the weight force. Basically, we're talking about a horizontal surface. If your object is not on a horizontal surface, this generalization will not hold true, and we'll discuss that in a later unit. Also, if the body is not accelerating in the vertical direction, this generalization will hold true. Now, what am I talking about? Well, our next video we're going to talk a lot about it, and we're talking about elevators. You accelerate in the vertical direction, thus altering this relationship here. However, if you're talking about anything resting or even moving in a horizontal direction, this generalization will hold true. Our normal force will always be equal and opposite to that of our gravitational force. So now let's talk about our third and fourth types of forces. We've got friction. Everybody's heard of friction. Friction is defined as the resistance of a body sliding over a surface. In other words, if you are pushing something, if you're pushing a giant refrigerator, let's say, there's friction that's opposing your direction of push. So, the friction force runs parallel to the surface. Our normal force ran perpendicular to the surface. Our frictional force runs parallel. So if we are attempting to slide this particular object to the right, so this is our force applied. This is our force that we're using to try and slide this particular object to the right. Our frictional force points in the opposite direction. And the way that we depict frictional force is by F sub F. So this is our frictional force or force of friction. Again, our units wind up being newtons. So things that you want to think about: frictional force is always opposing our direction of motion. Normal force always opposes our surface. So our normal force would be pointing up here, and our force of gravity would be pointing down there. If I can make a G. There we go. Our fourth type of force that we're going to be talking about would be tension. We really don't talk much more about tension. We talk a lot more about our normal force and our frictional force and, of course, our weight force in later units. But our force of tension, this is pretty much all we really cover. But what is tension? When a cord or a rope or even a rigid body is pulled taut, so pulled tight, it's said to be under tension or experiencing a tension force. Now, our force of tension is depicted, yes, you probably guessed it, Ft. So this is our tension force. And again, our units wind up being newtons. The cord is actually considered to only be a connection between the bodies and serves only to transfer the force. Now, what do we notice about our forces of tension? Where you are pulling and where that cord is attached, our force points towards the center of that particular cord for every single force here. How you calculate force of tension depends upon how you're going to be pulling things. If it depends on the type of motion that you're going to be dealing with. Okay. But tension always points towards the center of that particular cord. So now, what I want you to do is our independent practice for free body diagrams and normal force and gravitational force. So again, free body diagrams, things I want you to really think about. Okay. Let me just show you an example. This really doesn't have all that much, it doesn't have anything to do with these particular problems. So I'm going to just cross that out just so you don't get confused. But I'm going to show you free body diagrams, FBD. If we are on a horizontal surface, so here's a table and here's a block, sure. Free body diagram. Let's just say we're dealing with our force applied. we want to move in this direction. So here's our force applied. So that is what we're actually depicting here. So here's our free body diagram over here. We've got our dot representing our actual object. Let's just say we're moving at constant velocity. We know that if we're dealing with constant velocity, that means we're not accelerating. If we're not accelerating, that means we have no unbalanced force. So, which means I'm going to have to move my dot a little farther over. So here's how you would draw your free body diagram. First, we're going to take our applied force. Let's just say our applied force is moving in this direction, so we've got force applied. Hopefully I can fit it all. Yeah. So there's our applied force. Next step, because we didn't say that we were on a frictionless surface, we would have friction opposing this motion. Since we're moving at constant velocity, that means that our frictional force, our arrow, must be the same size as our applied force arrow, because that means that these two forces are equal and opposite of one another. We're moving at constant velocity, so these arrows must depict the same magnitude force, just in opposite directions. Next, every single object will experience a weight force. So I'm going to make it just a smidge smaller, because not all of these are equal. Let's just say our weight force is slightly smaller than our applied force. Since we're on a horizontal surface, that means that we are experiencing a normal force. Now our normal force is equal and opposite to that of our force of gravity, because we're not accelerating in the vertical direction. We're actually simply moving horizontally. So let me put this in terms of numbers for you. So let me cross this out so you don't get all confused on that. Okay. Let's just say that our applied force, we are dealing with an applied force of 1,000 newtons. And our object has a weight force of 500 newtons. Okay, so let's draw our free body diagram down here. So our applied force, the arrow, is going to depict our 1,000 newtons. Our force of friction must also depict 1,000 newtons, because we're moving at constant velocity. So yes, the object is moving to the right, but the frictional force is equal and opposite. Next, we've got our force of gravity, which should depict, I don't know if I left myself enough room, but it should be half the size of that arrow. And we've got our force of gravity equals 500 newtons. And again, because we're on our horizontal surface, we have our normal force opposing this. And again, equal and opposite. So we can generalize, and we can state that our normal force is equal to our negative force of gravity, opposite, equal, and opposite. And we can state that our force applied is equal to our negative frictional force. Again, now where did I get the negatives? That's just depicting that it's moving in the opposite direction. Our free body diagram already depicts that it's moving in the opposite direction. So just be aware of that's how you would draw a free body diagram. Make sure you read the particular questions, really think about it. These ones are intended to get you thinking about elevator physics and our next video. So try these all on your own with this in mind, and I will see you for our next video.